Very much for inviting me. So this is joint work with Nishant Mehta, who just joined the University of Victoria. So he's also sitting here in this room.
Peter, it's a little hard to hear you back here.
Okay.
Yeah, this mic is working.
Use this.
Yeah.
Okay. So this is joint work with Nishant Mehta, who just joined the University of Victoria. He's also here in this room. Now, what is this about? So this is about excess risk bounds. That's kind of an alternative to the generalization bounds you've seen in the previous talk. So here the goal is, these are oracle bounds. So they tell you how fast you learn, in the sense that you have a set of predictors. You want to learn a good predictor from the data. And it says like, how fast do you converge to the best predictor in your class? But the bounds are very similar to the type of PAC-based bounds we've just seen, and there's similar mathematics, and they are often also studied by PAC-Bayesian people, and they also have the familiar KL complexity term. So these give clean bounds for randomized predictors, in particular also for so-called generalized Bayesian and Gibbs posteriors. So that's actually, we will see in a moment, that comes back to one of the questions we had, that like the bounds we get hold for any type of learning algorithm, but they will often be optimized if we take something very much closely resembling a Bayesian posterior. So there's already a bridge there. So that's nice, but these bounds also have weaknesses, and one of them is, so you will be more precise about that later, it's not very widely known. I think it was probably first noticed by Audibert. If you have really large classes, which is what people in statistical learning theory often like to study, basically polynomial bracketing entropy classes, then these bounds don't give you the right rates. So probably the algorithms you get are somehow not minimax optimal, or if you do get the right algorithms, you cannot really analyze them with these bounds. And then, of course, as nice as all this work is in learning theory, nowadays the Rademacher complexity approach is a lot more common. It has been very successful in the past. It's now become the standard approach in textbooks on learning theory. And Rademacher complexity bounds for learning are then usually also transferred to VC dimension bounds. And it's very unclear how they relate. So I would like to relate the PAC-based bounds to the, let's say, more well-known standard Rademacher bounds. Now then there's actually superficially completely different problem that I've been struggling with for about 15 years. And it's a very different setting. So the main setting of this talk is just like the previous talk. We have IID data, frequentist, coming from some distribution. But in learning theory, people also study individual sequence prediction, where you try to minimize some kind of worst case loss, worst case over all possible data sequences. And if you take the logarithmic loss function, then that becomes equivalent to a form of data compression. Now, within the data compression literature, there is a famous quantity called the Shtarkov integral, or the normalized maximum likelihood complexity. And that's, we will see later what that means. It's kind of measures how well you can predict compared to the best element in some class in the worst case. Now, if you look at the formula for the Shtarkov complexity, and we'll see it later, it somehow reminds you of Rademacher complexity. I've actually, in my book on MDL, more than 10 years ago, I conjectured that there should be a relation. And in fact, there is one. I found it. And it helps me to go back to the first problem and then basically solve two different problems in one fell swoop. So what we do is we bound the excess risk in terms of a new complexity, which generalizes the PAC-Bayesian complexity, by which I mean basically the KL from posterior to prior, which you've seen in the previous talk. It generalizes both that and the NML complexity. And it does, so depending on the type of estimator you use, and something we call a luckiness function, you get either the PAC-based complexity or the NML complexity. So the luckiness function is a generalization of the concept of prior, which, just like the prior in the PAC-Bayesian world, determines, like, so you get bounds which depend on the data you get, and it determines for what data you are lucky. For some data, the bound will be better than for others. If your prior assumptions were right, if you work with Bayesian type of priors, if your prior assumptions were kind of right on the mark, you will get a better bound with the PAC-Bayesian approach. This is a generalization of that. So it somehow encodes prior ideas about the data. If they turn out to be correct, you get better bounds, but the bounds always hold, whether your assumptions were correct or not. Now we get this NML complexity bound, and we can further bound that in terms of Rademacher complexity. So I've got a new bound there. And once we do that, then we get the optimal rates for these large classes, which is kind of the weakness of the PAC-Bayes approach. With large classes, you don't get these optimal convergence rates. So if you don't understand this, don't worry, because it will get clear as we go. So, but I couldn't resist, because this workshop is about both Bayes and PAC-Bayes, to say a little bit about where I come from. So I'm actually somebody who is both in the Bayesian and the ML community. Actually, tomorrow there's a Bayesian conference starting in Texas, and I'm going there. And I've been obsessed with Bayes and model specification and generalized Bayes since about 2011. So what do I mean by generalized Bayes? Well, we have a set of densities, and then if eta is 1 in this formula, it's just a standard Bayesian posterior. So think of f as a name for your probability density. Pi 0 is a prior. So I only look at IID models. So P sub f is the density of an outcome, z, and the posterior is proportional to the prior times the likelihood. But we look in generalized Bayes at eta not necessarily equal to 1, mainly smaller than 1. So if you take eta smaller than 1, here you get a generalized updating procedure which puts more weight to the prior and less to the data. With eta 0, the posterior is just the prior. And then I'm also looking at Gibbs posteriors, which are a further generalization of this. So now f is a set of predictors, usually functions from x to y. We have some loss functions. Function L sub f. So in many cases z will decompose into x and y, and then we could have, for example, the squared loss or the 0,1 loss. And then the Gibbs posterior, or further generalized Bayesian posterior, is just the density of f given the data is proportional to e to the minus the loss. So the better f predicts on the sample you have, the larger its posterior. So you can do this with any loss function, also with a logarithmic loss function. So then z is not decomposed in x and y. And what you get then is that you have there e to the minus eta minus log density of z under f. So the e and the log cancel. And then actually, so for the log loss, the second problem reduces to the first. So you can also think of it as a further generalization of Bayes, where now you don't have a posterior over this probability distributions, but a posterior over predictors. I've done a lot of work actually with several co-authors in this direction. Relevant for this talk is it started with something I call the safe Bayesian, which was a method for learning this learning rate, this exponent eta, automatically from the data. Why is that important? Well, in another paper, which has actually just recently been accepted to Bayesian analysis, we show that if your model if you have a probability model, so we're really in the Bayesian framework, but your model is wrong but useful, and if you use standard Bayes, you can actually sometimes get disastrous results. We had a previous result like that with John Langford in the early days, 2004, but that used a very concocted, weird model. Now we show that the same thing can happen just for linear regression. So then it's important to take, if you have misspecification in your Bayesian, it's sometimes really important to take eta smaller than 1, because if you take eta smaller than 1, then these problems typically go away. And the risk bounds I present will explain to you why eta smaller than 1 works. I've also worked on this learning eta with various co-authors in an individual sequence non-stochastic setting. And this year I had 2 papers with Nishant. I'm going to talk a little bit about both, but mostly about the second one. So now we're getting to the core of this talk. And actually both of these new papers are about extending an existing PAC-Bayesian bound type excess risk bound due to Tong Zhang. So Olivier Catoni and Olivier have similar bounds, which are in some sense even stronger, but it will pedagogically be by far the easiest if I explain our work in terms of Zhang's work. So the remainder of this talk will be basically just about this formula, which at this point will look very complicated, and I will guide you through it slowly. So this is Zhang's excess risk bound, and once we understand that, we can work towards generalizations. So it is important to pay attention the coming few minutes when I explain this. And it looks daunting now, but I will slowly make it more palatable. So what does this bound say? So we have IID data from Z1 to Zn. And then see. The bound holds for arbitrary learning algorithms at output distribution. So this P hat M, which is an abbreviation of this, could be a Bayesian or a generalized Bayesian posterior, but the bound holds for arbitrary learning algorithms, but they actually, special cases when they put all their probability mass on one particular F, then they're just like, for example, empirical risk minimization or maximum likelihood. They're deterministic. But they can also output a distribution over F like Bayesian estimators do. Everything is allowed here. We have a prior distribution on F, so, but again, this thing holds just like the PAC-Bayes bounds for any prior you like. It's always true. And then it says something about how something you learned from the data and F you learned from the data will tend to behave on future data. So the two papers Michel and I wrote, actually one of them is mostly about the left-hand side of this equation. And I will have to talk a little bit about that as well, because it also gives relation between Bayes and PAC-Bayes. But I'll mostly talk about the right-hand side, where you see there's a KL here. I'll explain in a moment more about it. That will be replaced by a new, much more general complexity measure. So, more about the bound. First, this strange inequality sign. What does it mean? Actually, it's an abbreviation we introduced, and it means that the inequality holds both in expectation over a sample and with very high probability. What does that mean? Well, formally this just means this. So it's the expectation of the exponent of the difference is smaller than 1. Now, what does that mean? Well, if you use Jensen's inequality, that implies that the expectation of x is smaller than the expectation of y. If you use Markov's inequality, once you have that exponential moment bound, it implies that for every positive number a, the probability that the left-hand side is larger than the right-hand side by a is exponentially small in a, where gamma gives you how fast the exponent decreases. So what is stated there, this Sang's inequality is both an inequality in expectation over training samples of size m, right? So if you put an expectation on the left and on the right over samples of length n is true, it also means that the left-hand side is with very high probability not much larger than the right-hand side. So that's the first thing. Now what are we bounding here? That's the quantity RF. So RF is defined as LF minus LF star. So L can again be any loss function, in particular squared loss or 0,1 loss, or the logarithmic loss. And if it's a logarithmic loss, then Z is typically not decomposed as X and Y. It doesn't matter, this always works. Now, LF of Z is the loss that predictor F makes on outcome Z. But we subtract from that the risk minimizer. So the risk minimizer, for simplicity we assume it exists, is the element of your set of predictors, your model, which minimizes the expected loss. So there are many things in F, some of them are good, other bad, and F star is the best one. Right? That's the one you want to learn. So what happens here is we look at the empirical average over the Fs that we learn from the data. How well do they perform on the training sample? And that is basically, we bound how well they perform on a new test sample. So this Z here indicates a test sample. We bound how well they perform in terms of how well they perform on a training sample, where you might overfit, plus a complexity term. Because you might overfit here, so you can expect this to be not smaller than this, but you need something extra. So to clarify that further, let's look at a simplified case where we look at a learning algorithm which always outputs a single distribution. That's equivalent to having a probability distribution which puts all its mass on one distribution. Think, for example, about the loss minimizer, or with log loss and maximum likelihood. So in that case, things simplify. You don't get an expectation over F because the posterior puts all its mass on one particular point, F hat. F hat is an estimator. So in this simplification, it looks like this. So you have the expected risk of the F you learned based on the training set. So this is your training set. And forget about the n here, so that's weird. I'll go back to that in a moment. Think of this now as just the expectation. So z is a test example, so the expectation over a new test example of the f you learned from the training example is bounded in expectation and probability by how well the same f performed on the sample it was based on, plus a complexity term. So this is just the KL complexity term you get if you have a posterior which puts all its mass on f hat. So this is just a specialization of Zhang's theorem, and it shows you one of the weaknesses actually, because this only works if you have f hat takes values in the countable subset. Otherwise, this KL term goes up. So one of the extensions we will show is that you can extend this to the case even with deterministic estimators and not restrict to a countable subset. So this is a special case, right? We don't have this complicated expectation over the posterior here. If we would have expectation here, then it would be clear what this means. It would mean that the expected loss, so that's the risk of the f you learned from the data, converges relatively fast to the best possible thing, because this thing in general will tend to go to 0. This, if eta is not too small, will go to 0 as 1 over n. So this means that this thing will be kind of, the thing you learned from the data will in the future behave almost as behaved on the sample you had. So the risk, the expected difference between how well it behaves and the best thing you can do in your class goes to 0 quite fast. Yeah?
I think it's difference of eta or different
So that's the, I'm going to explain that. So this, I haven't explained that yet. I told you that ignore it for now. It would be great if we didn't have that, because then we would have a real excess risk bound. The excess risk of the thing you learned is small. Right? But of course, there's a problem here, because there's this anneal thing. So more general, if we have learning algorithms that output a distribution, which we'll call posterior, even if it's not Bayesian, then what the theorem says is we don't just have f hat here, but now we draw from the posterior and we look at, again, forget about the annealed for now. Just think of it as the expectation of this on a training, on a test outcome. If we draw from this thing we learned from the data, from the posterior, then on average, over our draw, we will have, our excess risk will be small, or at least it will be close to how the same f's performed on the training set, plus a complexity term. But now the elephant in the closet, we don't have the real excess risk, we have the annealed risk on the left. So what is that? Well, the annealed risk is defined like this. It's some kind of exponential transform of the actual risk. And of course we really want to know the real excess risk. So this is not good enough yet. Now actually it's easy to show that the annealed excess risk is always a lower bound on the actual excess risk. But that's not good enough, because in general it can even be negative. And indeed, the theorem as stated here holds for every eta without any further conditions. So it can't be right, it would be too easy. And indeed, this annealed risk can in general be negative, and then this becomes an empty result. However, under the right choice of eta, where this right choice depends on basically the true underlying distribution and the model f and the loss function and how they interconnect, for the right choice of eta we can actually also, the annealed risk also upper bounds the actual excess risk times the constant. The constant is never 1, because the annealed risk is always smaller than the actual risk, but it can get pretty close to 1, so they become comparable. If we're working with a log loss, then our algorithm, actually our learning algorithm, outputs a distribution over probability densities, right? We're more like in the standard Bayesian scenario. And then actually we're often happy with getting a bound in terms of the Hellinger distance rather than the actual risk, which is a bit easier. And because this thing is a bit closer to Hellinger distance than to excess risk. So let me give an example of that. If you do log loss and you have a well-specified probability model, so well-specified means that the model is correct. And in this notation it means there's a true distribution P. The risk minimizer is P sub f star. So if the model is correct, this means that P of f sub f star is equal to P. The the best thing in your model is actually the true distribution. The true distribution is contained in your model. That's the case that statisticians typically look at. They just hope or believe that they're in this case. If you're in this case, then for any eta smaller than 1, actually the Hellinger distance, which is also the standard distance that statisticians work with to bound the performance of estimators, like Bayesian or maximum likelihood estimators, the Hellinger distance will be larger than a constant times the Hellinger distance, and then the bound becomes meaningful for density estimation. And in fact, you can retrieve standard theorems for Bayesian posterior concentration, which have been very influential in the Bayesian community, or I should really say frequentist Bayes, because again, they assume that the data comes from a distribution, so that's frequentist, but they assume the distribution's in their model, and they check like how fast does the posterior converge to the true distribution. So one of the most well-known theorems to this respect is by Bosch, Goossen, and van der Vaart. And basically, we can retrieve their results. We get the same results under much weaker conditions as soon as we take eta smaller than 1. So in a way, for a real Bayesian, we're cheating because we have to take eta smaller than 1, and they have eta as 1, and the price they pay for that is basically 3 extra conditions on the models for the results to hold. So let me show that to you in more detail. So this is again Zag, right? You know this holds in general. And now we take a well-specified probability model and we take eta smaller than 1. Then, by the previous, you can replace this annealed thing by the squared Hellinger distance between the true distribution and f you learned from your data. And this thing is a difference of log losses. So it's the difference of minus log probabilities of data. So that's actually a log likelihood ratio. And there's the complexity term. So here's a bridge between all this work and Bayesian inference. Actually, if this holds still for every estimator, but if you plug in the generalized Bayesian estimator for eta smaller than 1, you can rewrite the right-hand side. And the right-hand side, so the KL has this, like in the posterior, there's the Bayesian marginal likelihood is hidden there in the denominator. Everything works out nicely if you, several things cancel here. And in the end, you get a bound in terms of the minus log base marginal likelihood, which is this thing, again raised to the power eta, divided by the true density of the data to the power eta. Now and then, won't go into details, but you can bound that thing further. And basically, the more prior mass you put in the neighborhood, Kullback-Leibler neighborhood of f star of the true distribution, the better your bound gets. And in this latter form, basically the bound we have here becomes a generalization of the standard bounds you have in Bayesian inference. With the only condition we need is that this thing is large. So this prior is large in Kullback-Leibler neighborhoods, because then this thing will be small. If the prior is bad, then we get a bad bound. So this is exactly also a condition that is standard in Bayesian inference, but we don't, by using eta smaller than 1, we don't need any other. Condition on top of that. And this has actually also been noticed in the Bayesian community. There are several people who use this eta slightly smaller than 1, because then they need less conditions. Now what happens if your model is wrong? If your model is wrong, then basically in general, for etas things smaller than 1, things won't work anymore, but often, and that would be a different talk, there's no time to explain the details here, often there's still a critical eta bar, and if you take eta smaller than the eta bar, then this thing still works, but now you have a generalization of the Hellinger here. F star is now the closest distribution to the truth in your model in terms of KL divergence. So you still get a convergence theorem, just like before, but now under misspecification. But you do need this condition that there's this critical eta. And again, different talk will tell you where this eta comes from, but you can do it. That's actually, that's the paper I'm not talking about here. It's the other paper we finished this year. So that's about the log loss. So, and about density estimation. So what about general loss functions? For general loss functions, these Hellinger distances are not very meaningful. We really want an excess risk bound. So we have a loss function like squared loss or 0, 1 loss. And we want our theorem to tell us that with high probability, our learning algorithm will output distribution over f, such that if we draw from the distribution, we will be very close to f star in terms of the loss of interest. Our expected loss will be very close to the expected loss of f star.
Excuse me,
Yeah.
sorry about my ignorance, but could you tell me more about the Ellinger distance and how you have put it there? I don't understand how come the Ellinger distance comes out. Because it was on the excess risk, and as I understand, the Ellinger distance is the distance between distributions, so I don't know how.
Okay, so I can briefly, let's say, so if you look at this, so this is the annealed risk, and by definition that's an expectation of e to the minus eta times the loss, right? And then a logarithm of that. Now, if you have the log loss, then e to the minus eta times the loss is really a difference of the loss between f and the loss between f star. So that's a log of f star over f, where f star and f are densities. So you have e to the power log of f star over f.
Okay,
So the expectation is actually expectation of a likelihood ratio to the power eta. That's the annealed risk. And then you can imagine, if you know the definition of Hellinger distance, that also is basically, so this thing talks about minus log of the expectation of a likelihood ratio, and the Hellinger distance is 1 minus the expectation of a likelihood ratio. So if you do Taylor approximation of minus log, it's close to 1 minus, and you get this. That's so you want the actual risk. So now it turns out that if you have, like now you need it, in general you need a condition, because in general the annealed risk will be much smaller than the actual risk. So in previous work we introduced a condition which we call U central. And so U central tells you that, so F star is the best in your model, right? It minimizes the risk. And U central says that F star doesn't just minimize the risk in expectation, it also is very good with very high probability. So basically what this says is if you would have epsilon 0, it would mean that the probability that F star is really worse on an outcome than any other F is exponentially small in the difference. Right? So it says F star is not just best in average, but also with high probability it won't be much worse than any F star. But we have a little slack here. So this comes in various versions depending on how fast how this u depends on epsilon. So if you take u a constant, then basically if you take u a constant and you take log loss, you're back in the previous case. Then this really says that there's an exponential bound, but in general we will allow u that gets smaller as epsilon gets smaller. So basically this means that you allow a little bit of slack, but if you make this thing smaller, so if you make the inequality weaker, then the slack gets smaller. So again, it may sound, if you haven't seen this before, it may sound completely like new, but it works in the sense that if you assume this, then you can bound the actual excess risk in terms of the annealed risk plus a slack term. So it depends on like how fast u epsilon depends on epsilon how big this is. So now we make it concrete. If we plug this into Zhang's theorem, it now says, so if you have this u central condition, it says that the actual expected risk is bounded by this Zhang complexity thing, where eta now becomes this u of epsilon and you have the slack epsilon. So it turns out that this, for bounded losses, this always works with linear epsilon. It becomes a void condition, so it's always true for linear epsilon. So then you get epsilon here and epsilon here. Then you can optimize over epsilon, and you divide something by n times epsilon plus epsilon. So if you optimize, you get epsilon 1 over square root of n. And then you get something divided by square root of n here, plus 1 over square root of n here. And then you get an order 1 over square root of n rate, which in the literature is called the slow rate. So for bounded loss functions, you automatically get that here.
The constant c far away from 1?
You can actually, it depends on the loss range. So for bounded losses, it's a linear in the loss range. So in general, and this may be more well known to some of you, the central condition is not very well known, but it turns out for bounded losses to be equivalent to a Bernstein condition. And the Bernstein condition has been used in lots of works in statistical learning theory. Basically, if a Bernstein condition holds for your problem, and Bernstein condition refers to like somehow again how the true distribution and the loss function and your model interact. If a nice Bernstein condition holds, then you can get faster rates. So there are lots of papers about when you get learning algorithms not converging at 1 over square root of n, but faster. The fastest is 1 over n. And they typically say, like, assume that a Bernstein condition holds, which is often quite realistic. Then we can get faster rates. So U central turns out to be equivalent to Bernstein. If you have the Bernstein condition, those of you who know it, it looks like this. So it says that the second moment of this excess loss, expected excess loss, is bounded by just the excess loss to the power beta. So the best case is when this is 1. The worst case is when this is 0. And then for bounded losses, this just says that this thing is bounded, which holds void. It's void, it holds automatically. So the larger beta, the better the rate we get. And it turns out that if something like this holds, then you can retrieve with Zhang's bound the optimal rates for relatively simple models. So again, it would be, to explain all this in detail would be an entire talk. So you can also do things for unbounded losses, but I won't say anything about that. I want to say something about the right-hand side. So for now, even if this went too fast, just think of like everything on the left-hand side of Zhang works. We don't have the annealed risk there, we have the actual risk, right? Basically, by and large, that is what happens. The annealed risk can, in all cases of interest, bounded in the right way by the actual risk, which is what you really want to bound. So just assume it's fine, and then we'll talk about the right-hand side of the bound. So here's Zhang again, right? We have this annealed risk, now just think of it as a real risk. It's bounded in probability by what happens on the sample plus this KL term. So now our bound comes in. So we don't work with priors, we work with luckiness functions. So a luckiness function is a function on the whole sample, Z1 to Zn, and the set of predictors f to the positive reals. Now it turns out that for every luckiness function, we'll see later that priors are a special case. For every luckiness function, we have this result. So again, left-hand side is the same. Right-hand side, first part is the same. That's what the estimator f you learned from data, if you drawn it, did on the training data itself. Plus, now the KL term has been replaced by a general complexity term, and it has a data-dependent part and a data-independent part. The data-dependent part looks a little bit familiar already, like a KL part, because it's a minus log of this luckiness function. Now the data-independent part is new, and I'm not going to explain to you yet how it looks like, because I'm going to build this up slowly. So we will see later how it looks like, and we will start by looking at the simplest case of this new theorem, and from that we're going to build up how this S looks like. So we'll now look at a very simple case where we're going to take the learning algorithm not to be the base posterior, but to be empirical risk minimization. Just minimize the loss in the sample. So what will happen then? So in that case, we get this version. But if we take a certain luckiness function, if we take other luckiness functions, we will retrieve Zhang's bound. The new bound is a generalization. And yet other luckiness function will give us useful bounds to analyze things like the lasso or ridge regression. So it really depends on W and the type of estimator. So we'll start, as I said, with a very simple estimator, ERM. So for log loss, that would be maximum likelihood. You minimize log loss, you maximize the likelihood of the sample. And we take the simplest luckiness function, constant equal to 1. And in this part, we assume bounded losses. So what happens then is that, so this is the general Zhang's result, right? But now if we take deterministic f, this disappears again, right? We've seen that before, and we get, let's say, the real risk of the f hat you learned from the data is bounded by its average on the data itself plus complexity. So now we take constant w, then this is minus log of 1, we take w as 1, so this part disappears. So now it becomes, the complexity becomes data independent. Now we even simplify because we take ERM, so then this actually becomes smaller or equal than 0, because this is the difference on the sample between the loss of the thing you learned from the data and F star, the best one in your class. But if you minimize the loss on the sample, you're always better than F star. F star minimizes the loss on expectation, but F hat minimizes the loss on the sample. So the loss of F hat on the sample is smaller than the loss of F star. So now we actually end up with a very simple bound. Now it just looks like this, right? All the difficult parts have gone away. So how does S look here? So at first, again, it looks very complicated. It's the expectation of e to the minus 1 r f hat evaluated at the sample divided by something like the normalizer. Okay, so now we get to the core of the whole talk, because this looks very complicated until you do this. You have a set of predictors f, and now you map each predictor in your set to a probability density, q sub f. And this will simply be a re-weighted form of the true distribution. So we assume the true distribution has a density, p, that's where the data comes from, and we rate it according to f. So if f gives a high loss on the sample set and f star a low loss, so f is bad on set compared to f star, then the probability gets smaller, and if f is good, it gets larger, and you normalize so that if you integrate this over z, you actually get a probability density. So every f has now become q sub f, which is a probability density. In the special case where you use log loss and eta is 1, and the true distribution is in your model, so p sub f star is equal to p, then these qf's are just equal to the pf's. Then this transformation doesn't do anything. Your original f's were already probability densities, and they remain probability densities. But for eta smaller than 1 and general loss functions, you create something new. You had a loss function, you now make a set of probability distributions. Once you've done that, you can rewrite this as S is the integral over the probability density over all sequences of data that f hat, based on the data, gives on the data itself. This, of course, is smaller or equal than what you get if you would use the maximum likelihood estimator within this set of distributions. So this is bounded by q f hat of the maximum likelihood estimator based on the data, because the maximum likelihood estimator maximizes this probability, right? So this is always bounded by this. So now we've transferred our original set of predictors to a set of distributions, and log of S is this kind of maximized likelihood averaged over all data. So in particular, this is larger than 1, because if you would have a single f here, this would be 1, right? If you average over all data, you get 1 for probability density. But because you always maximize for each data outcome, you get something larger than 1. So now the miracle happens. So this quantity is actually, the log of this quantity is actually well known in data compression. It's the minimax regret if you do sequential prediction relative to the log loss, relative to the model of the QF densities. Again, no time to explain here what exactly that means, but it is kind of a central concept in data compression, where you have a set of distributions, and each of them defines a code to compress the data, and you try to compress the data as good as the best one in the set. So this thing is a known thing, and plays a central role in my earlier work. So this is intriguing, but it's not just intriguing, it will also be useful, because this thing then, in turn, can be bounded in terms of the Rademacher complexity. So this is the case for ERM. Now we're going to generalize a little bit. We're still going to look at deterministic estimators, but we're going to allow luckiness functions W, which depend on the data. So they're not just equal to 1 whatever f on the data, but they still don't depend on f, so they only depend on the data. So I call them simple luckiness functions. So then we get this form. So this is again f hat, deterministic estimator, and now you get a data dependency. And now log S, how does it look like now? Well, it turns out we get a simple generalization of the previous formula. Now, again, you define these new densities. Every f gives you a density. And now you integrate it over all data with the weight W. This actually is also known in the literature. This is, the log of this thing is something which has been called the minimax luckiness regret. It's basically kind of a reweighted minimax regret, which is used in settings and data compression where the original integral is infinite, which will happen in many cases. And now actually we have something which also works with unbounded loss functions. Because we can make sure that things, by choosing W in a clever way, we can make sure that this integral doesn't become infinite. So this now leads to bounds for penalized empirical risk minimization. If we take as our luckiness function W e to the power minus some penalization function. So think of f like in a linear regression. If f has a linear representation and you take the L2 norm, then the penalization would be just a squared error norm. And then actually, if you take that, then the right-hand side of the bound looks like minus log e to the minus penalization. So it's like if you take lambda as 1 over e, it's lambda times penalization plus a constant not depending on the data. So then the estimator, this holds for every estimator, but the estimator which minimizes the bound is actually the penalized empirical risk minimizer. So in this way you can get bounds for things like lasso. And you see that the role of the multiplier in lasso is very similar to the role of the learning rate eta, or actually 1 over eta in generalized Bayes approaches.
So doesn't W here depend on f as well?
It depends on the data, but so the thing is that if f hat is a deterministic function of the data, you can kind of hide the dependency on f, right? So in a way it does, but you can also rewrite it in a way where it doesn't. So we get bounds for things like the lasso. We haven't worked them out, but we're pretty sure they're sharp. In a moment you will see why. Final thing is now we go to the full generality. So now we use general random estimators which output a distribution again. And then it turns out that in order for the bound to hold, we have to generalize this S. So now it looks very unwieldy and complicated. Suffice it to notice here that if you have a deterministic estimator, then it collapses and you get back the previous formula. So this is the fully general formula which encapsulates all of them, and this is the fully general statement of the result. But now, if we have the fully general statement, if we have a prior, and we define the luckiness function to be prior divided by posterior given the data, then we can show that the S, the data independent part of the complexity, is always bounded by 1. And that's just very simple proof, just Jensen's inequality. So then, if we have a luckiness function of this form, this thing falls away, and we have here expectation of minus log W, which is the expectation of minus log prior divided by posterior. This is just the KL divergence. So now we have Zhang's bound back. So what happened here? We have one bound. Sometimes it specializes in having something on the right, which is called the normalized maximum likelihood, which plays a central role in data compression. Sometimes it has on the right-hand side a log marginal likelihood, and that also has a coding interpretation. So I was wondering, is there some kind of general link here with data compression? And it turns out there is. So basically what happens here is that every choice of luckiness function, up to multiplicative constants because they cancel, gives you a different bound, which prefers different data sequences over others. And it can also be interpreted, the right-hand side with some hand waving, it's a bit more complicated than that, but essentially the right-hand side can always be interpreted as a code length of a particular code. So there's kind of a 1-1 relationship between these luckiness functions, the bounds, and particular ways to code your data. Now, why is the bound sharp? Well, the bound says that this thing is smaller than this thing in a stochastic sense. So left-hand side bounded by right-hand side. So by definition, that means this. Now, if you look at the proof, which is actually very simple, it's just rewriting the proof, we actually prove that this holds with equality. So in that sense, the bound is as sharp as it gets. If you lose anything, it's only in later step when you kind of bound this NML or Bayes complexity in other things. Right? The bound itself really says that the left-hand side minus the right-hand side has this exponential equality. So no information is lost in this inequality which I stated in the bound. Now, given the time, I should probably skip the second part. I'll just say that so this complexity can also be bounded by the Rademacher So this is, if you do ERM, you get here this normalized maximum likelihood. And we have a second theorem which shows that this thing is bounded by the Rademacher complexity of a related set of functions. And there's a little slack term, but the slack term is so small that we actually, so we get this thing. It's so small that we get the optimal rates if we then further bound the Rademacher complexity in terms of entropy numbers. So in the end, if we have really large classes with polynomial entropy numbers in classification, so that basically means that if you make small covers of your model, then the size of the cover blows up exponentially, so that's what I mean by really large. Then, and if a Bernstein condition holds, so the data distribution is kind of favorable for you, you get this rate. So if beta is 1 over k Bernstein holds, and this is the rate you get. So this is the rate which appeared for classification in Sibakov's classical paper from 2004 for large classes. And I've always been bothered by the fact that you can't reproduce this, so he uses a lot of complicated empirical process theory and chaining, so it's a mathematical technique, which you can't really use with PAC-Bayes. So now we managed to recover this old bound. And so we recover existing optimal bounds. We don't need to use localized Rademacher complexity, which is needed in earlier approaches to this, and which is super complicated. So as difficult as this looked, it's still simpler than the localized Rademacher complexity approaches. We only use standard Rademacher complexity. So that's it. Thank you very much.
Thank you very much, Peter, for this very nice talk. We have time for questions. And Peter, could you please repeat the question?
Of course.
Briefly.
So, just to clarify, this luckiness function, is it evaluated at the actual data or on the data drawn from your randomized estimator?
It's evaluated on the actual data. Well, it appears in two places. It appears in this S, and there is an expectation over all data. So it's like averaged over all data. And then the data-dependent part is just evaluated at your training data. Yeah.
So I might have missed this, but the excess risk is defined by the difference between the classifier you're focusing on and then some fixed classifier. Is that right, the difference?
Right,
So is there anything to be gained by looking at different functions of those two values? Like ways in which PAC-Bayes bounds have been generalized to look at it?
Definitely. So I think that's like Catoni's turf. So I've seen papers like by you, I think, where you don't look at directly at the excess risk, but by some nonlinear transformation of it, which is kind of helpful for if you have like fat-tailed distributions and so on. So that could be done, yes. Yes.
Thanks. So, like, what, if any, takeaways do you have for designing new learning algorithms in the patient setting?
Okay, so the question is what takeaways I have for designing new learning algorithms. That's of course a very good question. Okay, I might say none. The thing is, this is mostly, as it stands, this is mostly like trying to understand how different approaches to, like for existing learning algorithms, like generalized posteriors, like lasso, like empirical risk minimization, how they kind of all hang together. Like, are there single underlying principles, single notions of complexity? So in that sense, it's really just like trying to understand what exists better. However, I'm not saying that this might not change, because there is this thing, the luckiness function here. And so that gives you an enormous amount of freedom in basically every different choice gives you a different bound. And all of these bounds, some of them will be good for this data, some of them for that data. So actually, this might lead you, just like some choices, I mean, if we would first have had this, and we wouldn't have things like penalized ERM, we would say, okay, if we take this luckiness function, then this is the right estimator to use. and we get a good bounce. So maybe for new choices of luckiness, you get new algorithms, but I don't know yet, right? This is just, we just posted on archive, so.
It seems that you can also have a complexity notion on data. Do you have thinking of comparing it with VCD or anything like that?
Yeah, actually, so that is, I didn't talk about it, but that is in the paper. So basically you can further, this also works with empirical entropy numbers, and then you get the things with the VC dimension on the right-hand side. So you can do it, but I just didn't talk about it. So it's flexible enough for that as well.
Maybe last question. At the early stage, are you using Fenchel duality somewhere? It seems to be.
That's actually a very good question. So the question is if we're using Fenchel duality or things like Donsker-Varadhan change of measure theorem. And the answer to that is intriguing and tricky because the thing is you can do what you can, if you look at the original Donsker-Varadhan, which you talked about, where you get a KL term, you can also do that by using Jensen's inequality in a funny way. You get the same result. And so basically, for this general result, in a way our result is what you get if you don't use Jensen's inequality, but just keep the left-hand side equal to the right-hand side. So you just rewrite it in a clever way so that it looks more palatable. So therefore we don't use change of measure and we don't use Jensen, we just kind of have a kind of equality there.
Okay, thank you, Peter. So we now have a coffee break, and you're also welcome to look at the posters by the end of the room. Next talk is at 11 in 30 minutes. So, and coffee break is in the lobby, just outside the room on the left.